is the collection of multiple types of data for the comprehensive and holistic approach of an archaeological site. When we talk about the coastal zone and shallow submerged archaeology, we see human presence along Mediterranean coastline from very early period. So coastal environments since antiquity consist favorable areas for the development of early human habitation, providing vital resources, facilitating trade and communication, and offering strategic advantages that support urbanization. So because of that, from very early times, people choose coastal zones as places to live and to carry out daily activities. However, due to environmental and geological processes, many ancient coastal landscapes were gradually submerged, and as a result, a large number of archaeological sites are now located underwater, either partly or completely. So now, typical examples include a harbor installation, settlement remains, and certain shipwrecks. And this represents both portable and non-portable cultural heritage. And now in Greece, underwater archaeology and marine geoarchaeology are relatively recent fields comparing to terrestrial archaeology. And for many years, research focused primarily on ancient shipwrecks, while in recent decades, this has been increasing interest in shallow submerged coastal sites, providing invaluable knowledge for the interpretation of past human civilization and highlighting the cultural importance of underwater cultural heritage. So, however, the study of these sites face a major methodological challenges in terms of survey and documentation. So traditional approaches, whether from terrestrial archaeology or from underwater archaeology and marine geoarchaeology, often fall short when applied to shallow submerged contexts. Nevertheless, the investigation and study of these sites is extremely important as they constitute the bridge between the land and the sea, and they provide valuable information about human activities close to the shoreline and how communities interact with sea and communicate with other places. So in a way, these areas represent the front door of a settlement opening from the land towards the sea. So what is this methodological gap that limits the study of the coastal and shallow submerged archaeological sites? We can identify two main factors. The first concerns to environmental and anthropogenic conditions. Environmental conditions are related to specific characteristics of each area. These include weather-related factors such as wind and wave action, which strongly affect sediment mobility. So as you can imagine, sediments can either expose or bury archaeological remains. In addition, water movement can cause erosion and can lead to the gradual destroy and scattering of archaeological remains. And anthropogenic factors are linked to the fact that coastal zones are still areas of high human activity today. And such examples include maritime traffic, both commercial and private, anchoring practices, recreational swimming, and tourism. So people may damage archaeological remains either intentionally or simply out of curiosity by disturbing, removing, or altering archaeological material. At the same time, there is often strong construction activity, especially in the island environments. So, moving to the second factor that limits the research related to the technical constraints. The traditional diver-based surveys also face several limitations because shallow submerged sites often cover large areas and from such a close distance, a diver cannot easily perceive the spatial relationship between structures, while the field of view is very limited. So let's say it is similar to standing too close to a large and complex painting in the museum. And when you are very close, you cannot see the overall composition. So this is therefore a major limitation. There are also concepts related to diver safety, physical endurance, and the need to cover large areas and the requirement of large teams with increased cost and resources. But now, beyond the diver-based surveys, traditional marine geophysical surveys rely on instruments that often operate at the limit of their specification in very shallow waters, and the performance is reduced either because of their size or because of signal distortion in shallow environments. And also, in addition, these instruments are usually heavy and are deployed from vessel with a deep draft, which cannot easily approach very shallow areas. So finally, photogrammetric documentation of shallow submerged sites, whether from the sea or from the air, faces additional limitation. These are mainly related to light refraction, water-inducted distortion, and reduced visibility, since we are dealing with the high-energy environments, which is important to understand that calm conditions ideal for research purposes are really rare. So overall, shallow submerged archaeological sites constitute a methodological gap because they are too shallow for conventional underwater archaeological or marine geoarchaeological methodologies and too submerged for terrestrial approaches. So as a result, these areas are affected by limited visibility, restricted spatial perspection, and the lack of standardized and scalable protocols. So now let's move on to our case study and the development of a methodological approach. Naxos is located in Greece, in the Aegean Sea, and it's a part of the Cyclades island complex, where it occupies a central position. It is the largest island of the Cyclades in terms of surface area, and the site of Grotta is located in the northwestern part of the island, where the modern town and the commercial port are situated today. Now, our study area is divided into two sectors. Sector A referred to Grotta and Sector B referred to Northern Port Basin. And the majority of the archaeological remains are found in very shallow waters between 0 to -2 meters in depth. Now, additional areas of archaeological interest are recorded more sporadically and at greater depths, reaching approximately -4 to -5 meters. Now, in terms of physiography of the area of Grotta, is exposed to strong northerly winds for most of the year, and the average annual wind speed is around 4 × 4, while a wave height can reach approximately 0.7 meters, which is more than half a meter. And in these images, we can see a very typical situation in the study area, when conditions can change very quickly, even with a few minutes, shifting from calm weather to extremely challenging conditions. So now imagine to have a research permission that lasts only a few days and meet this kind of weather. It is, in this condition, it is unsafe even to enter the water, not a word for a systematic archaeological fieldwork. So regarding the research background of the area, terrestrial excavations at Grotta have been carried out for more than 30 years, and the material is still being studied today. And here it's the red cycle, the excavated area. And as part of these excavations, An underwater inspection was also attempt to complement the full study of the site. However, it did not continue due to adverse weather conditions and the limited resources and technology available at the time for studying such a site. Now, to better understand the archaeological importance of the site, let's briefly look at the continuous settlement phases through the centuries. So, archaeological excavations brought to light material remains, portable and non-portable, that reveal the long and complex history of Grotta Naxos, making the site as one of the most significant palimpsests of the Aegean region, with almost uninterrupted residential phases from prehistory until today. More specifically, earliest human traces dated back to Neolithic era, showcasing a significant insular society that evolved into a thriving settlement in the third millennium. Now, during the early Cycladic period, Grotta flourished as evidenced by both the architectural remains and the extensive cemetery on the nearby hill of Aplomata here. And while the Middle Cycladic period is less documented, with only a few scattered ceramic sherds around the shore. But the next period, the late Cycladic period, and specifically in its late phase, marks a peak of residential activity and development with the establishment of two successive settlements with Mycenaean character noted for urban organization. And also the chamber tomb cemeteries at Aplomata reflected the noble and extroverted character of the Naxian community, as well as the dense networks of contacts and mobility among the Aegean. Now, in the following period, Grotta was Grotta was abandoned and became a cemetery during geometric period, with inhabitants moving to the fortified hill of Castro, a few meters to the south. And during to the Archaic period, despite the limited archaeological evidence from the settlement itself, indirect sources attest to prosperity at the 7th and 6th century BC, marked another peak of economic and political flourishing of Naxos and its city, which emerged as a maritime ruler and a dominant power in the Aegean. Now, the classical period saw a setback due to the Persian invasion in the 5th century, but the city gradually recovered and after several centuries, Grotta gained its urban character. During the Hellenistic period, Grotta developed into a financial center with significant urban changes, a transformation that continued into the imperial period with periodic reconstructions. While the medieval times marked the final phase of the ancient activity, with the medieval castle constructed over the ancient fortification to the hill of Castro, leading to the modern city of Naxos. So now that we have an overview of the of the archaeology of the site, let's move on to my research focusing on methodology. This slide outlines the methodological framework proposed for the documentation and mapping of shallow water submerged archaeological sites, and the main methodological framework I followed used downscale approach, which moves from the general to the specific point of interest. The workflow is structured into three main phases: the planning, the mission execution, and the post-mission processing. And it begins with the definition of the mission scope and the collection of the existing information, followed by sensor selection and mission planning. The fieldwork phase focuses on systematic data acquisition and quality assessment, while the post-mission stage involves data processing, validation, and visualization of the final results. So together, these steps constitute the base of an integrated approach, ensuring accurate spatial documentation and exploration of the site. Following the research plan, the study area was divided into two sectors, as we said. Sector A, which refers to Grotta, and Sector B, which refers to Northern Port Basin, for a comprehensive investigation of the coastal marine space. Now, together, these sectors cover an area of 90,000 square meters, which is roughly equivalent to the size of 10 football fields. To survey this area, we designed 33 survey lines that are followed by our robotic vessel with line spacing of 5 meters. This layout ensures that the instruments provide 100% coverage of the area for the accurate and detailed mapping purposes. And finally, the speed of the vessel through the survey, that is also very important for optical data quality from both sensors, fixed at 1 knot. Moving to the instrumentation, the platform used for the survey is a tailor-made unmanned surface vehicle called otherwise USV, and it is a small catamaran measuring 1.7 meters in length and 1 meter in width, with a payload capacity of 20 kilos. And this USV is equipped with a GNSS receiver for the navigation and the spatial data reference, which obtain high accuracy of over 3 centimeters, a compact side scan sonar, a single beam echo sounder, and an underwater camera. Together, this instrumentation forms a miniature version of the equipment typically used in offshore research, adapted to meet the specific needs of the shallow water site. In a way, a USV is a small-scale model of an oceanographic research vessel and its instrumentation. So this setup allows us for complete and detailed mapping, as we said, for the seabed. And the important thing is that these techniques are non-intrusive and non-destructive to marine antiquities. Now, a few words on how the geophysical instruments work and why we select them. First of all, side-scan sonar is an active acoustic imaging system widely used for seafloor mapping and seabed characterization. This instrument sends acoustic pulses to both sides of the survey path and record the intensity of the returning sound from the seabed surface. And by stitching together these returning signals, produce a high resolution and a high metrical accuracy two-dimensional image of the seabed morphology and acoustic reflectivity patterns. So the high-intensity backscatter is generally associated with harder or denser seabed materials and objects, and while the low-intensity returns indicate softened sediments or less reflective surfaces. Moreover, through the acoustic backscatter imagery, we can infer the shape, the size, the texture, and the spatial extent of seabed features. For example, in the image to the right, the different seabed textures appear in two-dimensional sonograph, which provides information on material differences. As we mentioned, darker tones corresponding to lower backscatter, typically of sand, and high and brighter tones indicating high backscatter from harder substrates such as stones. So overall, we use side-scan sonar because detect acoustic anomalies that contains all the mentioned characteristics, which they help us to discriminate whether the features on the seabed are likely natural or human-made, and also because it is a very quick way to accurate at a centimeter scale survey technique. Moving to the single beam echo sounder, it is also an acoustic sensor used to measure water depth directly beneath a survey platform. This instrument determines depth by transmitting an acoustic pulse and measuring the two-way travel time of the sonar reflected from the seabed. The particular advantage of this system is that it can operate effectively even in very shallow waters while maintaining high depth accuracy. So this instrument, it collects depth measurements continuously along the survey track, and these measurements are then combined to produce the final bathymetric map of the area. And now that we've seen the methodology we applied and how this instrument works, let's move and see the results. Starting with bathymetry, we observe that the seabed develops differently across the two sectors. In the Grotta area, sector A, the bathymetry slopes gradually down to about minus 3.5 meters. And at this point, the smooth slope stopped by a sharp drop, forming a steep down to minus 5 meters, while after the seabed continuously gradually again, as we can see also this step in the photo. It is important to note that this break occurs almost along the horizontal axis that seems to extend across the entire length of the beachfront. And now, in addition, Sector B, near to the Monterey Harbor, the seabed shows a uniform and gentle slope along the coastline. In the central part, only two elevated seabed features mark the transition between the shallow and deeper zones, and depth in this area ranges from 0 to minus 7 meters. Now, to better visualize these abrupt changes, we created inclination maps, and these maps can clearly highlight the points where sudden variation and sudden variation are, and depicted also in the bathymetry. So here we can see the side scan sonar mosaic. Now you can think of it as a photograph of the seabed, but with different colors instead of natural. And everything you see here reflect the composition and texture of the seafloor. So more specifically in Sector A, Grotta, we observed a large rocky area extending along the entire length of the beachfront. This zone shows multiple breaks, holes, and features related to biological and geological erosion. And on top of this surface, there is a large number of stones visible as a chaotic pattern across the area, while elements of different size and shapes covering most of the study area. Um, Most of these stones appear to be human-made remains, although in some parts, especially in the northern area, natural seabed features are also present. So we also notice that this rocky surface ends suddenly, and beyond this point, in the deeper zone, here, some become the dominant seabed type, characterized by a uniform and darker acoustic pattern. Now, in the Sector B, despite its close proximity to the Sector A, the seabed presents a completely different picture. There is an almost total absence of rocky surface. The area is dominated by sand seabed, showing darker tones and a homogeneous texture. In this mosaic, in the eastern part, this is have a uniform pattern, which is interrupted by biological features, which with round shapes. here. Uh, to the west, we observe a rougher surface which corresponds to the elevated seabed features mentioned earlier and likely represent the natural seabed substrate. Sorry. And in the southern part of the sector, at this point, there is a high concentration of material, and this material shows clear spatial distribution and suggests deliberated patterns rather than natural accumulation. Now, using ground truthing for cross-checking the side-scan sonar mosaic, I classified the different seabed features based on their reflectivity, texture, and geometry into 13 main categories. The use of underwater camera played the key role in confirming the geophysical data and identifying seabed feature as biological, geological, and human-made. So together, these categories describe the overall composition of the two study areas, and from the basis for the seabed classification, and is the basis for the seafloor classification map. Now, these 13 categories leading to the construction of the seafloor morphology map. And this map shows the clear boundaries of each category. It helps us to understand the spatial extent of the archaeological remains and how they are distributed across the seabed. And in this way, every bottom type, which means a different material of the seabed marked with a different color. So this map also help us to understand how complex is the composition of the seabed, something that is not easily to understand only with optical methods. So after identifying and classifying the various types of seabed material, we created a map of archaeological targets. Across both sectors, identified a total of 9 structures, as shown in the picture marked with Latin numbers. And these targets represents clearly defined and recognizable archaeological structures. So here again, ground truthing helps us to confirm that the submerged structures are made of different type of material. For example, in one case, we identified worked stones, while in other we have assemblages with non-worked stones. So these targets are classified as archaeological structures based on two main characteristics, which are their geometry and their coherency. So more specifically, they appear either as linear features or as larger structures with clear boundaries. Let's move to the sector A. In sector A, at the beach of Grotta, within the area where the archaeological remains are found, we can basically identify two zones. The red zone, which is very shallow from 0 to minus 0.5 meters, contain a large number of stones without a clear arrangement. And this matches with the what we saw earlier in the mosaic, where the pattern appeared chaotic. And the green zone at the depth between minus 0.5 to minus 2 meters contains the best preserved and most clearly identifiable structures. More specifically, the structures in the Grotta area shows a clear linear pattern along an east-west axis, and they share very similar characteristics. All of them are built with square stones of approximately the same width, and they are all located at depths between -2 and -2.5 meters. and this gives the impression that they are part of a single structure that once extended along the entire beach front. In all cases, the construction consists of two parallel rows of stone blocks, although in some areas these rows are no longer fully preserved. While the structures appear to belong to one continuous feature, they do not survive in the entirety, as we said. So there are gaps, and in several places the stones are scattering. And this pattern is likely the result of a later natural process and human activity that affect the sites over the time. So in the deeper zone of sector A at around -5 meters, there is a notable arrangement of large unworked stones. These stones are located in the central part of the beach and placed close to each other, and their position appears deliberated rather than random. Now I am moving on to the sector B. Three structures were identified, which are concentrated in the southern east part of the area. The structures differ in form from those in the sector A, while the depth at which they are located range from 0.5 to -3 meters. Um, Now, in the first case, we observe a pile of unworked stones arranged in a bow shape, and this feature is scheduled to be published in the coming months and has been identified as the medieval harbor of Naxos. The second structure is closer in form and construction to the features observed at Grotta. It is located at the depth of around -2 meters, which matches the depth of the Grotta structures, and it lies beneath a stone pile of unworked stones. The concentration of these unworked stones represent the third human-made structure. It was identified as such based on its arrangement and orientation, which appears also to be deliberated rather than natural also. So now to complement the geophysical data, I also tested a visual method for creating 3D models. So we have two models. The two best documented structures are one from the sector A and the other from the sector B. And using 3D modeling allows us to better visualize the geophysical results and gain additional information about the specific characteristics of the structures and potential state of the preservation. And in second case, which exhibits a more complex morphology, as you can see also in the shown graph, the 3D visualization helps clarify the structure and support the overall documentation by improving our understanding of the complex seabed. So, in summary, the methodological framework we developed and applied using Grotta as a case study, a complex area in terms of both seabed morphology and archaeological remains, highlights the critical role of multi-leveling mapping. Now, the combination of acoustic and optical sensors enable high accuracy mapping by simultaneously capturing different types of information and approaching the study area in a holistic way, while at the same time, all the methods used are non-invasive and non-destructive to both natural and archaeological features of the seabed. So, this increased their applicability in many different environments. And in addition, it is especially important that marine remote sensing have the ability to provide rapid data acquisition and facilitated multiple remote data analysis without restrictions on time or location, because as we have seen, time is critical in coastal environments, so these methods offer a major advantage in the field. But of course, every method has its limitations. And in our case, we could not survey the very shallow water zone from 0 to minus 0.40 centimeters because even with the USV vessel, it is dangerous to approach areas with scattered stones, which could potentially damage the instrumentation and also the antiquities. And at the same time, cold wind conditions are crucial during the marine geophysical survey to avoid wave action and obtain good quality data. So now in the future, we plan to further enhance this methodology by integrating additional tools, including the development of a multi-camera photogrammetry rig to support higher resolution optical data acquisition that will help us to identify potential relationships between structures, particularly in the areas where mosaic patterns appear chaotic. So overall, we believe that this approach, combining multiple data sources for mapping shallow submerged sites, is a key methodological approach which can be applied to similar sites and still has a room for improvement. That I'm continuing to work on it on my PhD research. So thank you very much.